So, uh, Hello, I am Pranjal Chauhan. I am from IIT Guwahati, and I am going to review a paper called Firefly, Scalable Ultra Accurate Clock Synchronization for Data Centers. It was published in ACM Sigcomm 2025 by these authors. Now, the goal of this paper is clock synchronization. So, in a data center, each device has its own internal clock, and these clocks are not identical and they need to be synced uh, with each other. So, there are two types of synchronization, internal and external. Internal sync means all devices inside a data center agree on a common internal clock, whereas external sync means all devices synchronize to UTC, which is Coordinated Universal Time, which is the global standard time reference. Now, why does clock synchronization matter? Let's say, for example, a cloud hosted financial trading system. So, in financial exchanges, time directly affects money. So, even a tiny nanosecond delay changes who buys, who sells, and who profits. So, that's why clock synchronization is very important. So the goals of this paper are sub 10 nanosecond internal accuracy and sub 100 microsecond external accuracy. Now we see limitations in prior works. First, the hierarchical systems protocol like NTP and PTP. So they have a tree-like structure where devices at level 1 sync to a master clock, devices at level 2 sync to level 1 devices, and level 3 devices sync to level 2, and so on. But the master clock introduces a single point of failure, and this also introduces error cascades where if a clock at level has an error, then all levels below that also have error. And also this scales poorly. Uh, then second, we have centralized systems like Huygens. Here, many devices synchronize directly with a central clock, but the problem here is that the system avoids changing clock too aggressively, so it slowly adjusts clock rates over several seconds, and while waiting for slow changes, clocks continue drifting, so error accumulates. And then third, there is specialized systems like White Rabbit. It achieves sub-nanosecond synchronization with the use of specialized hardware, but the problem is its cost. It is costly, so it can't scale very well because we have to put in our money. Now we see how devices measure time differences. Suppose there are two devices A and B which want to sync clock with each other. So the key goal here is to calculate offset. Offset equals clock B time minus clock A time. So these devices exchange probes. First, A sends a probe at time TA and B receives a probe at time RB. One-way delay here is the time it takes to go from A to B. Now offset equals RB minus TA minus one way delay. But the catch here is that to measure one-way delay correctly, clocks must be synchronized, but also that we need synchronized clocks to correctly calculate one-way delay. This is like chicken and egg problem. So to avoid the need of synchronized clocks, we use RTT. This is the time it takes a packet to go from A to B and then return from B to A. We use RTT because it only needs one clock to calculate it, which is A start timer and A end timer. So uh, for we can say for ideal network conditions, we can say that one-way delay is approximately RTT by 2, and hence we can calculate offset. Uh, but when we consider one-way delay equal to RTT by 2, it is only for ideal network scenario where we consider forward path delay equal to backward path delay. But real networks are not symmetric. Forward delay is not same as reverse delay. We call this asymmetry error. Asymmetry error can come from two things. First is path level asymmetry, where lengths of route of forward forward route and backward route differ in length. Second is component asymmetry, where individual hardware devices in between add unequal delays, which can accumulate. Then we see network jitter error, which a probe experiences while traveling in network. So two primary reasons for these are: first is queuing delay in switches. Second is timestamp variations, which are caused because commodity hardware timestamps are noisy and can fluctuate around 10 nanoseconds. Next, we see clock drift error. So what happens is every device has an oscillator which generates periodic ticks. The OS counts these ticks as time value, but no oscillator is perfectly stable. Some oscillator can run slightly faster or slower, making time values differ. We call it clock drift. Now there are two types of clock drift. First is static drift. It is caused by manufacturing error. It can cause clock to drift by parts per million, but it is easier to correct because it's predictable, so devices can calibrate. Then second is dynamic drift. It is caused by things like temperature, aging, and LN variance. It can cause clock to drift by parts per billion, smaller compared to parts per million in static error, but it is also harder to correct. Now we come to external synchronization challenge. This figure explains how UTC time enters data center. First, the GPS satellite broadcasts global UTC timings, but this can cause hundreds of nanoseconds of error already. GPS feeds this value to oscillator, a highly stable local clock. Atomic oscillator generates one pulse per second, which is highly precise pulse used to synchronize hardware clocks to UTC. But many commodity NIC cannot consume this signal, so it must pass through CPUs and PCI buses, which adds microsecond level jitter. And then finally, the UTC timestamp reaches NIC, which spreads it throughout the data center. So as we can see, by the by this UTC timestamp, by the time this UTC timestamp reaches NIC, it's already error prone. Now we come to the core concept of Firefly, which is distributed clock consensus. Here, each node probes neighboring nodes to calculate offset and drift, average all those values received from neighbors, and updates its own clock. And then Firefly uses random consensus graph. Firefly probes d-random neighbors from anywhere in data center instead of just local neighbors. Um, So it probes any D random, whether they be neighbor or not. And advantages of this is first, lightning fast convergence because clock information spreads globally very quickly. Second, reduce static error because probing different nodes creates measurement diversity, which cancels out biases of path asymmetry. Third, high scalability because D scales logarithmically with number of nodes. Now, Firefly splits synchronization into two separate layers, which are internal synchronization and external synchronization. As you can see in the figure, the blue dots are NICs. After internal sync, they converge to SVC, which is Swarm Virtual Clock, which is internal consensus time. Then Firefly moves this SVC towards UTC. Now, this figure shows UTC itself is stable, but time servers which spread UTC in data center are noisy. Meanwhile, SVC is stable. Now this figure shows how synchronization traffic flows. Blue lines are for internal probing for SVC. Red dotted lines are for external probing to time servers to sync to UTC. As seen, all devices do internal probing and calculate average, but only few devices do external probing. Now we come to probe exchange. This is how Firefly actually measures clock differences between NICs. Firefly executes a four-packet exchange. So suppose we have two NICs A and B. First A sends to B, then B sends to A. So at this point A records TA and RA, B records TB and RB. Now A sends this TA and RA values to B, and B sends this uh, uh, TB and RB value to A. Now both NICs have all values TA, RA, TB, and RB. They can use this to calculate offset and drift. Now clock offset is not constant because oscillators drift, offset changes over time. The blue points here are offsets, which are noisy because of jitter or asymmetric error. Firefly collects many offset samples and fits a line through them via linear regression. The paper also uses a sliding window here, meaning they only use recent offsets for measurements. So by doing this, drift rate is calculated as change in offset divided by elapsed time. Now we come to three clock layers. This is how Firefly separates different notions of time inside NIC. So first is hardware clock, which is actual physical NIC clock. Second is SVC dash, which is swarm virtual clock. This is NIC's local estimation of averaged consensus time. Third is UTC dash, which is virtual UTC clock. It is NIC's estimate of UTC time. As you can see from the figure, each NIC has its own local SVC estimate. Next, we come to rapid consensus. This is algorithm by which Firefly updates its SVC dash clock. SVC dash is designed to achieve consensus by as quickly as possible. Whenever an NIC exchange probes, it sees that its neighbors are has different SVC average, so it shifts its one SVC towards that value by a fraction. Now to handle anomalies, Firefly does truncated meaning it discards extreme values before averaging. Suppose the offsets are 2, 3, 4, 5, and 100. So Firefly discards lowest value, which is 2, and highest value, which is 100, and averages only 3, 4, and 5. So now we come to gradual percolation. This is how Firefly updates real hardware clock. The SVC clock updates aggressively. The physical clock would jump if it just copies SVC value, making it inconsistent. So instead of directly jumping, Firefly changes the clock rate, meaning it speeds up or slows down the clock slightly. This is called percolation. Uh, so we have understood syncs. We have understood syncs happen between SVC and hardware clock. But what about UTC, the external time? So, as shown in figure, there are three clock layers in each NIC. In UTC layer, only a subset of NIC contact external time server and is distributed to every node through consensus. This UT is synced with SVC through percolation. This is similar to how SVC is determined through consensus and is percolated to hardware clock through percolation. This figure shows that UTC dash layer is noisy and unstable. SVC dash layer is more consistent and hardware clock is most consistent. Initially, all these differ, but as time goes on, all these converge. Um, this this provides massive scalability because only a fraction of devices send synchronization traffic to external time servers. Hence, the massive stability. This graph shows that with only 20% of NICs probing external sync, uh, Firefly remains consistent even with 2048 NICs. Now, Firefly tries to mitigate measurement errors from queuing jitter. First method is transparent clock (TC). If switch hardware supports TC, then switch can directly measure the time the packet took in its queue. By calculating this, queue delay can be subtracted from calculations. But the catch here is not all switches support TC. Then we come to next method, which is RTT filtering, used when TC is unavailable. Here, Firefly assumes smallest RTT sample experiences minimum queuing. So it tracks base RTT as minimum recent RTT, which acts as an estimate of network delay. So after doing this, Firefly keeps only those probes whose RTT is less than base RTT plus some threshold and discards other probes. Now, during heavy congestion case, every packet experiences queuing delay, so minimum RTT itself rises. So Firefly chooses the smallest RTT sample within 2-second window as base RTT. Now this is how Firefly tries to mitigate measurement errors from path asymmetry, which is forward delay not being same as backward delay. First method to this is peer-to-peer TC, which is advanced extension of TC. In here, each switch measures exact physical link delay for each link, and that value is put into the packet. When this packet reaches receiver, receiver can calculate path delay. And the second solution is path patrolling. It is used when switch does not support P2P TC. Here, data centers often use ECMP. Firefly sends test probes with random flow levels to explore multiple paths, and for each path, RTT is calculated. The lowest RTT path is the one with the least asymmetric error. Then Firefly only uses those flow levels for synchronization traffic. Finally, we come to results. First, the evaluation methodology. Authors deployed Firefly to 48 machines connected in 6-hop data center network. They used an external hardware tester called XGA to test efficiency of Firefly. So XGA is capable of extremely accurate packet timing, hardware timestamping, and nanosecond level measurements. XGA monitors 60 NICs using direct hardware timestamping. Now we come to baseline synchronization accuracy. As seen in graph, the 99th percentile synchronization error was only 10 nanosecond for internal and around 400 nanosecond for external. This meets the required goals of 10 nanosecond internal accuracy and 100 microsecond external accuracy. Others compare Firefly to industry standard PTP boundary clock. So Firefly outperformed PTP-BC since it achieved 10 nanoseconds across 248 NICs with 6 hops distance. Meanwhile, PTP-BC has 12.5 nanosecond error across 4 hops. Now, Firefly has massive scalability as shown in graph. As number of nodes increase, P50 and P90 stays consistent. The error barely changes. This graph shows to maintain errors less than 10 nanosecond, only around 5 to 10 pairs are needed even for thousands of NICs. For error less than 5 nanoseconds, we need roughly 12 to 30 pairs, still manageable, so it scales massively better. Now we come to Firefly's resilience under drift error, as shown in the graph. Even under large static drift, plus minus 20 ppm, Firefly maintained roughly 8 to 10 nanoseconds P99 sync error. So Firefly handles static drift very well. As for dynamic drift, others compare Firefly with Huygens R. As the dynamic drift increase, error goes beyond 200 nanoseconds for Huygens R. For Firefly, it stayed near 2040 nanoseconds, which is massive improvement. Now we come to Firefly's resilience under traffic load. As you can see, with each TC, Firefly under 95% load only has around 8 or 9 nanosecond error. But without TC hardware support, Firefly falls back to RTT filtering, which still handles error very well under 60% load, but it cannot handle 95% load very well. Now we come to path asymmetry resilience. We see very high error increase, hundreds of nanoseconds without uh, uh, without path profiling. But with Firefly's path profiling error is reduced to less than 20 nanoseconds, which is a huge improvement. Next, this graph shows the benefits of layered synchronization. Researchers injected increasing jitter into external time servers, but even after increasing jitter, the P99 internal sync error remained around 8 to 10 nanoseconds. So the system is highly stable. Now we come to limitations of this paper. First is Firefly cannot remove systematic hardware asymmetries. Second, mitigating errors depend on TC hardware support, which older switch hardware may not provide. And we already know if TC is not supported, Firefly uses RTT filtering, which does not perform very well under a high network load. And finally, Firefly is designed for tightly connected data center environment. It leaves much improvement for other types of networks such as wide area networks. So Firefly represents major shift from traditional synchronization systems and achieves high nanosecond precision with high scalability. Thank you.